So in trigonometry, there are three basic functions that we're going to be working with like so much that you're going to get tired of them. Before we introduce sine, cosine, and tangent and their definitions, let's get some geometrical ideas down together. When we are talking about an angle, we're going to represent angles with Greek letters, usually theta. Theta is like a circle with a line through it. It is a Greek letter, theta. We might also use alpha or beta. So when you see me drawing a Greek letter or a weird looking letter, it's representing an angle. Okay, and in this class, angles are always going to be presented on a coordinate grid in standard position. And what standard position means is it means that the positive x-axis, this business right here, is the beginning part of your angle. It is always the initial side of your angle, the positive x-axis. We are then going to rotate counterclockwise around our coordinate grid until we reach what's called the terminal ray, or the ending point of your angle. The amount of angle that we move is theta. Theta can be an acute angle. Theta could be a right angle. Theta could be obtuse. It could be straight. It could be larger than 180. It could be larger than 270. It could even go all the way around and be larger than 360. So what we're going to do is we're going to always make sure that our angles are starting on the positive x-axis and reaching a terminal ray in some quadrant. Now, once we start doing that and we start rotating our angle around a circle, we can create a whole bunch of trigonometric relationships between the location of these points that are at the end of our terminal ray. So given an angle in standard position and a circle centered at the origin, there is a point P where the terminal ray intersects some circle. Sine of theta, that's our first vocabulary word for today. Sine of theta is the ratio of the vertical displacement of P. Vertical displacement means up and down distance. Vertical displacement from the x-axis and the point P. So sine of theta is defined to be the y value, which is how high we are, our vertical displacement, divided by the radius length. Now the radius is the same everywhere, and the radius is a distance, so radius is always positive. Even if we're taking our radius into like a left direction, radius is always positive. Cosine of theta, which, by the way, I don't think I've said this yet this class, one of my biggest mathematical pet peeves is calling these things sin, cos, and tan. If you call them sin, cos, and tan, you owe me a quick book. They are sine, cosine, and tangent.
Wait, can you say that?
Sine, cosine, tangent.
Didn't I just say that earlier?
Don't say sin, cos, and tan.
Can we just say one of them?
Well, when we're referring to them, you would say sine of something or cosine of something or tangent of something. Just don't say sin, cos, or tan.
Why not?
Bothers me real bad. That's not their names.
Sin,
Quick buck.
tan.
That's another one. You're just racking it up over there, Shane. Okay, so cosine of theta is the ratio of the horizontal displacement of P from the y-axis and the distance between the origin and point P, meaning cosine of theta is defined to be x divided by r, where x is the horizontal displacement. If you're sort of remembering trig functions from geometry class, you probably learned SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Same vibe. It's just that we have put our triangle on a coordinate grid. So now instead of using the words opposite, adjacent, and hypotenuse, we can use the horizontal displacement, vertical displacement, and radius as our legs and hypotenuse of this triangle. Last but not least, we have tangent. Tangent is defined to be the slope of the terminal ray. We're going to highlight that one. The slope of the terminal ray. Since it's a slope, it's a rise and a run. And since rise and run represent the vertical displacement divided by horizontal displacement, we can define tangent to be y over x. Vertical displacement divided by horizontal displacement. Or, more appropriately, tangent of theta is equal to sine of theta over cosine of theta. So we have these three definitions for sine, cosine, and tangent. Tangent has two definitions, but you get it. These are going to be things that I need you to memorize because sine, cosine, and tangent are the basis of all trigonometry that we will do in this class. We need to know that sine is the vertical displacement divided by r, cosine is horizontal displacement divided by r, and tangent is the ratio that creates the slope of that line, rise over run. And if we know these things, we can answer a lot of questions, like perhaps something like this. It says, the figure shows a circle with a radius 5. Ooh, radius. Let's highlight that with our radius color, which is green. Radius of 5 centered at the origin with an angle measure of theta in standard position. The terminal ray of the angle intersects the circle at point P. We want to find the following values. Here's how we read a diagram like this. We need to find theta. Here's the symbol for theta. The little circle inside here tells me that theta starts here, bloop, goes all the way over here. That is the angle we're using. It's a really, really large angle. We need to know the coordinate of point P so that we can get a triangle created and we can do our trig. Here's my question for you. If this point right here is 3 comma 4, what's this point right here?
It's 3 negative 4.
3 comma negative 4. Let's go ahead and write that in. This P is over 3 and then down 4. It's like it's been reflected over the axis. They're the same distance away, which means my horizontal displacement, how much did I go side to side? 3. My vertical displacement, how much did I go up and down? 4. I went down 4, right? Down 4. And we know that my radius was how much again? 5. We have all the sides of this triangle that's created in the fourth quadrant from my angle theta as it loops all the way around. Because we have a horizontal displacement, a vertical displacement, and then our radius, which is the same all the way. If we have all of these things, we can answer what sine, cosine, and tangent is. Sine of theta is defined to be y over r. What is y? Negative 4. What is r? Positive 5. So sine of theta is the ratio negative 4/5. Yes? Okay, what about cosine? Cosine is defined to be horizontal displacement, or x, over radius. So what's the x value? 3 over 5. Nice, we get it. What about tangent?
The complicated one.
That complicated one. Negative 4 over 3. Nice. We're just using the definitions given a coordinate point around our circle. We can find x, y, and r. Before we flip the page over, are there any questions? Now, in this class, we are going to measure degrees. Hello. We are going to measure angles not in degrees. In geometry class, you probably used degrees. When I teach my dual credit classes, we will also use degrees. But in this class, we are measuring our angles with a different unit. The unit we are going to use in this class is called a radian. Radian is a measure of an angle. And we're going to discuss radians in depth with our coloring activity later. But when we're talking about a radian, it is a ratio of the arc length to the radius of the circle. So let's go ahead and circle this guy. Radians is the ratio of the arc length, which is like the crust of a pizza would be arc length, to the radius of that same circle. That gives us a radian measure. Just like we know things like 360 degrees make a full circle, we know a lot of information about radians themselves. In fact, if we remember that all the way around a circle is called the circumference, do we remember that word? The formula for circumference is 2 pi times r, which is 2 pi times radius. Therefore, what is the angle created by a complete revolution of one circle? So the amount of radians in one revolutions would be the ratio arc length, which is circumference all the way around, divided by the radius, which is r. Now look at that. There's something we can simplify out here, right? We can take the r out. R is going to cancel, which means there are 2 pi radians in every revolution of a circle. 360 degrees is 2 pi radians. So y'all remember those questions on your homework where it was like looping like this and I made you use some pi's without telling you what it meant? That was 1 complete rotation of a circle because it was 2 pi radians. Okay, just getting on the same page. Angles in standard position that share a terminal ray are called coterminal, and they differ by a number of revolutions. In science class, I know that revolutions and rotations mean something different, especially when you're talking about like planets and stuff. In math class, they're interchangeable. Revolutions, rotations, same vibe. Cool? I also need you to know that the direction in which we are moving around our circle is important. If we are moving in a positive direction angularly, we are moving counterclockwise. Counterclockwise. The negative angular direction on a coordinate grid is a clockwise direction. And since we are using coordinate planes to define angles, and that would mean that these angles kind of loop over and over again, they have a periodic phenomenon and periodic behavior because they're going to keep coming back and forth to the same values. So when we are learning about trig, we are learning about the periodic phenomenon that we introduced last class. But what we're going to really make sure we understand today is the concept of these radians that I'm going to make you measure in. That's our main focus for today, besides knowing sine, cosine, and tangent. In example 2, for each of the following, it says, sketch a picture of the angle described based on a unit circle and label multiples of each angle around one revolution of a circle. We want to draw pi over 2 in the counterclockwise direction. This feels like a lot, but stick with me. If I go all the way around, what was that measurement again? 2 pi. Everybody put 2 pi right here. All the way around would be 2 pi. So if I only went half the way around, 1 pi, because I would do 2 pi divided by 2, cut it in half, it would be pi. I also want you, and I know this is going to be annoying for a while, I also want you to write 2 pi divided by 2 down. If I didn't go 2 pi, and if I didn't go a full pi, I only went here. If this is pi, how much is this? 1/2 of pi, right? So we're going to call this pi over 2. This angle right here, theta, is pi over 2 in the counterclockwise direction. Because I know where I'm going with this, I also want you to write down 2 pi over 4, because 2 pi over 4 is pi over 2. Okay, question for you. All the way around was 2 pi. Halfway around was pi. A quarter of the way was pi over 2. This was 2 over 4. This is 2 over 2. What would this angle be if I ended up all the way down here? 3 pi's over a half, so it would be 3 over 3 pi over 2. 1 pi over 2, 2 pi's over 2, 3 pi's over 2. Let me do that again. 1 pi over 2, 2 pi over 2's, 3 pi's over 2. Cool, right? So our quadrants, quadrantial angles, are all like multiples of pi over 2. Pi over 2, 2 pi over 2, 3, I'm going the wrong way. Pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, which reduces to 2 pi. Stick with me. This time, on letter B, we're going to draw pi over 4 in the counterclockwise direction. So here's what I remember. I remember that all the way around was 2 pi. I remember that halfway around was pi. Let's write these numbers with a denominator that matches this question. Let's write it with a denominator of 4. If I wanted to change this denominator to 4, what would the number be up here? So that it is still 2 pi.
0.2.
I heard it. It would be 8. What's 8 divided by 4? 2. So it's still 2 pi, right? What if I wrote this number with a denominator of 4? And I still just wanted it to be pi. 4 over 4, right? We said earlier that this was pi over 2. What if I wanted to write that with a denominator of 4? 2 pi over 4. So here's my question for you. We want 1 pi over 4. If this part right here is where we're starting, and so it's essentially 0, and up here is 2 pi over 4, where would 1 pi over 4 be? Kim's doing this with her hand. What does she mean? What are you trying to tell me, Kim? Because I like it. Tell me more. Like down here?
In the middle?
What do you mean by middle? Middle of what?
The circle.
Okay, I'll say it again. This is 0. This is 2 pi over 4. Where would 1 pi over 4 be?
Like
At the bottom? In between what? In between these two, yeah? Okay, so with your pink marker, what I want you to do is I want you to draw a diagonal line from the origin as close to center as you can in that first quadrant. This value right here would be pi over 4. We have to be able to divide our entire circle, all of these 2 pi's, by different denominators, is what we're doing here. So if this is straight up north, the 90-degree angle, yeah, is 2 pi over 4, 1 pi over 4 has to be in the middle. So here's my question for you. This is 0. This is 1 pi over 4. This is 2 pi over 4. If I drew a line right here, what would it be called?
3.
3 pi over 4. Let's go ahead and draw that. So we have 0 pi's over 4. We have 1 pi over 4. We have 2 pi's over 4. We had 3 pi's over 4. We've already written 4 pi over 4. What would be the next mark if I did this? 5 pi over 4. What would this one be? 6 pi over 4, which, by the way, reduces to 3 pi over 2, which we found earlier. If I gave us one more marking out there, what would that one be called? 7 pi over 4. And then we make it all the way up, it's 8 pi over 4. We've now cut our entire circle into pi over 4 multiples. We're getting a slice of the pie, absolutely. We're going to keep slicing this pie, by the way. The next way we want to slice it, we have sliced it by pi's over 2. We have sliced it by pi's over 4. We're this time going to slice it by pi's over 3. So let's do it again. Yes, sorry. So this time we're going to slice it by pi over 3. Here's what we know. We know all the way around is 2 pi. We know halfway around is pi. We know a quarter of the way around is pi over 2. We know this is 3 pi over 2. We're going to get used to putting the quadrant angles there. This time, however, I only want a third of pi. If this is pi, where would you draw a third of it? I think I'm hearing what you guys, okay. With your green marker, we're going to draw like a little business right here because we want to slice the top semicircle, the top pi, into 3 slices because it's pi divided by 3. In which case we can label these as, well, I really did a bad job of slicing that one. Let me try to do it again. With the right marker, Miss Quigley. That's a little bit better. This would be 1 pi over 3. This would be 2 pi's over 3, which means the full 12 slices? So if we look, my semicircle on top has 3 slices. 1, 2, 3. If we go and keep doing this on the bottom, I should have 3 more pieces down there. 1, 2, 3. Let's label them. If right here is 3 pi over 3, what would this one be? Okay, let's count it again. 0. 1 pi over 3. 2 pi's over 3. 3 pi's over 3. 4 pi's over 3. 5 pi's over 3.
6 pies.
And 6 divided by 3 is? 2. Ah, nice. Okay. 4 pi over 3. 5 pi over 3. And this becomes 6 pi over 3. And 6 divided by 3 is 2. The up and down ones? Yes, and in fact, I know you can't erase because I don't have whiteout, but if I were to white out this, it would make it easier to see that they're equally spaced. Do y'all see what I mean?
Yeah.
Is that better? Okay, last one that we're going to slice this by. Oh, I'm waiting. All right, this time we're going to slice it pi over 6 in a counterclockwise direction. Yeah, I heard the deep sigh, and you're right. Here we go. We know that all the way around is 2 pi. We know that halfway around is pi. We want to slice just the top section, the pi section, into 6 pieces. Okay, great question. We want the top section to just be 6 pieces. So we're going to slice it like this. We're going to go boom,
Yes, that's fine.
boom. Sorry, I was using a highlighter. 1, 2, 3, 4, 5, 6. Assuming that I did those a little bit more accurately so that they are actually evenly spaced. I have 6 pieces along the top. If we were labeling them, they would be 1 pi over 6. What would be next? 2 pi over 6. What would be next?
3 pi over 6.
And then,
4 pi over 6. 5 pi over 6.
yeah, you're getting it.
Oh,
And then,
I'm getting it now.
okay, see, there was the light bulb we were waiting for. Can we do the bottom one?
Yeah,
Okay. Again, we're going to slice the bottom semicircle, if you will, the bottom pi radians into 6 units. And we label them. After 6 pi over 6, we would have,
7 pi.
and then
8, 9, 10,
9 pi over 6, 10 pi over 6, and 11 pi over 6. Now here's the deal. We have a lot of even numbers on this particular one that we're working with here. If we look at those even numbers, specifically looking at like this one, 2 pi over 6, what does that reduce to? Pi over 3. Oh, which means it's actually the green line from the one over here.
Okay, don't complicate it.
No, we're going to complicate it.
No.
Look, if we reduce this fraction, we get pi over 3, which means this line is in the same spot as this line. Oh. This is for musical? You're welcome. If we keep reducing these numbers all the way around, 4 pi over 6 becomes 2 pi over 3. Same spot as our pi over 3. We've already done 6 pi over 6, which is pi. 8 pi over 6 becomes 4 pi over 3. Again, one of my green lines. 9 pi over 6 becomes 3 pi over 2, which is what we started with in that first example. 10 pi over 6 becomes 5 pi over 3, a green line. And then 2 pi, which we could also write as 12 pi over 6. So why are we doing this?
No idea.
Great question. I'm so glad you asked. We have these 4 separate circles that have been all sliced in different ways. What if we lay them on top of each other? They're not all necessarily equal, but the colors are going to create a nice looking circle for us. So on your back page, I want us to add those same numbers around this whole circle because we are going to show the different important radian measures all the way around a circle, leading us into 360 degrees, but remember we're not using degrees in this class, into radians. So let's go first with our pink color. Actually, I lied. Let's go first with our quadrantial angles. So when we're starting off, this is 0 radians, and then we had pi over 2 radians, and then we had pi radians, 3 pi over 2 radians, all the way back to 2 pi when we go all the way around a circle. Those are our quadrantial angles, multiples of 90 degrees, if you will. Multiples of pi over 2. Now let's take our pink line, and any pink line we made on the other page, we're going to add to this document, which means we're going to have a pink line going flat. Those are multiples of pi over 2. We're going to have a line going straight up. And we're going to have our lines that cut our quadrants directly in half, creating 4 spaces on top and 4 spaces on bottom. Which means we have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. The green one is separating into 3 spaces on top and 3 spaces on bottom. Make sure you're paying attention to which one I'm highlighting because I don't want you to mess this up. We will highlight the flat line. We will not highlight the straight up and down. To split the top section into 3, I'm going to follow this line and this line, which means this one and this one. That would make pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3, 5 pi over 3, and 6 pi over 3, which reduces to 2 pi. The last one that we're going to do is the blue pi over 3. Pi over 3 does get the flat line, so you'll notice all 3 colors exist on the flat line. Then we need to split the top section into 6 units. So we're going to highlight basically all of the lines except for the pink ones. So here we go. We have this line. We have the green one. We have the straight up and down. The next green one. All green ones. And the flat one. And if we look at this, it becomes pi over 6, 2 pi over 6, which is green, 3 pi over 6, which is straight up and down, 4 pi over 6, which is green, 5 pi over 6, which actually gets to be blue, 6 pi over 6, which is pi, 7 pi over 6, which is blue, 8 pi over 6, which is green, 9 pi over 6, which is your quadrantial angle, 10 pi over 6, which is 5 pi over 3, and 11 pi over 6, until we make it to 12 pi over 6. Back again. These angles are the angles that are special all the way around our unit circle. They are the radian measurements that I need us to know information about. I also need us to be able to locate them around the unit circle. So eventually, if I ask you, where is 5 pi over 6, you should be able to visualize that 5 pi over 6 is in the second quadrant. If I say find 3 pi over 4, we should be able to visualize this angle here with the terminal ray. That's our end goal. It won't happen tomorrow, but it should happen the day after that. I'm just kidding. What? Commit to starting to memorize these angles. They are very important. And the reason that they're important is because they lend us to, and I'll scoot back to this if you need more copying time, they lend us to sine, cosine, and tangent along what's called a unit circle. The unit circle is going to assume that the radius length that we are using is a radius of 1. And if we have a radius of 1, that means all of our denominators for sine, cosine, and tangent kind of go away because dividing by 1 is kind of boring, which means sine gets to just be y, cosine just gets to be x, and tangent stays the ratio of y or sine over x or cosine. Our goal in trig, one of our goals in trig, is to be able to evaluate our sine and cosine and tangent functions without using a calculator. So we're going to need to memorize where all of these angles are along this unit circle so that we know where we are and what value I'm asking for when I ask for the sine of some angle. What's probably the most uncomfy for today, besides like literally everything, is the fact that I'm going to make you start measuring angles not in degrees anymore, but in radians. And again, what even is a radian? I'm so glad you asked. We're going to do a little arts and crafts moment to figure it out.